on the west coast of India. Nearly 100 kilometers from Mumbai, the town of Dolvi, where dreams are forged in the form of steel. A unique method, a mega-scale attempt, and risks that run large. Engineering and precision, making the impossible possible. Extreme Tech, the massive furnace replacement. India, a burgeoning economy. A giant, still in its infancy, growing faster than ever.
Today, we are producing almost 100 million ton of steel against total world production of 1,630 million ton.
No country can grow without consuming steel. Whether it is building bridges, roads, building.
The backbone of this young economy is steel.
We have to start consuming more steel.
And with 100 million ton, we are today in the third position in the world.
With real estate at the urban centers booming, the urban cover is expanding faster than ever. The country needs a steady supply of iron and steel.
Steel structures are much better than any cement structures. Because steel structure can last more than 100 years or so. Today, whatever structures have been made from steel 100 years back still are in use. Whether it is railway, whether it is transport, whether it is infrastructures, so everywhere if you see, the requirement of steel is going to increase tremendously.
Producers of steel are constantly trying to cater to this demand. And amongst the largest steel manufacturers of this country is JSW Steel.
Our contribution to steel industry has been close to 16 to 17%.
Today, JSW is India's largest steel producer. So we are a company which is technology-driven company. And we get very excited about new technologies and new ideas, and we are willing to take that risk. And many a times we suffer because of that, but most of the times we gain out of it. But we always think that, given the advantage of this technology, we have been a winner over the years. So therefore, we are always there to take new challenges, especially on technology front.
JSW has 6 steel plants located in India, which produces 18 million tons of steel per year. Its plant in Dolvi produces more than 3 million tons of steel per year and is one of the most dependable sources of steel for the company. One that has served them since 15 years. But now it's in need of an overhauling. The process of steel making is complex, but when broken down into the simplest flow is this. Raw materials like coke, iron ore and lime are taken through severe heat. Here they break down into molten iron and slag. This molten iron is cooled down, turned into different steel products and is then sold in the market. The most essential part of this process takes place in the blast furnace. The blast furnace is the heart of any steel plant. This is where steel is churned out. It turns raw iron ore into molten iron through a complex process. Once the blast furnace starts, it will run for the next 10 to 15 years continuously, stopping periodically only for maintenance. And after 15 years, this particular plant was in desperate need of a heart transplant.
In India, people they built a independent furnace and then they discard the old furnace and cut the furnace and then they take the new furnace in operation.
First blast furnace, this was commissioned in the year around 2000. It was already operating for 13-14 years time. It was due for relining. For relining, minimum shutdown required is 90 days.
A steel plant has three basic units: a stock house, a blast furnace, and a cast house. The raw materials make their way from the stock house into the blast furnace and come out of the cast house to be taken into the steel melting shop to be rolled out into sheets of steel. Sometimes plants have multiple numbers of these units. In case one of them shuts down, then the process can just be diverted to the remaining units. But Dolvi was a single-line system, which meant shutting the blast furnace would result in an immediate halt to production.
As far as the Western market is concerned, there is a considerable amount of demand from Bombay and around Bombay. Capacities of steel plants are still such that a shortage in the market of one producer would actually lead to a gap in the market, and it is not possible to import overnight. So therefore it would leave a space in the marketplace which would be harmful for economy.
We wanted to keep the shutdown to the bare minimum possible.
So when we have to take the shutdown for 90 days, was there any possibility that we can revamp this furnace and increase the capacity from 2 million ton, the old furnace, to 3.5 million ton new furnace? So there were several options which have been discussed. How to get this 1.5 million ton capacity from the new blast furnace.
And this 1.5 million ton boost with minimum stoppage in production requires nothing short of an engineering marvel. To figure out a way for the blast furnace replacement, the team decided to bring in some outside help. Help that came in the form of Nippon Steel and Sumikin Engineering Group, a steel technology consultant based in Japan who stepped in at JSW's behest, turning the project into an international partnership.
Nippon had done similar erection job, and when we talked with their erection engineers, I was really convinced that yes, they can do this job. And when it came to India, we sat together and then together we made a system, how it can be erected and how it can be done, the job can be done.
The team from Nippon and JSW discussed all possible options for the exchange.
There are 4 revamping methods: small piece method, ring method, large block method, and a single block method.
First, the small piece method. The blast furnace is taken apart part by part, and the new blast furnace is reassembled with new pieces in the same place. The shutdown period for this is around 150 days, which means loss of around 0.9 million tons of steel and around $90 million to the Indian steel market. The ring method. Here the old blast furnace is dismantled into horizontally divided rings. The new blast furnace is then erected with the newer rings and put in the place of the old one. Shutdown period for this is around 120 days, or a loss of around 0.72 million tons of steel and a loss of around $72 million to the Indian steel market. The large block method divides the old blast furnace into 2 large blocks. The new blast furnace is then fabricated into 2 large blocks and put together in the place of the old one. The shutdown period for this is around 100 days. That means loss of around 0.6 million tons of steel or a loss of $60 million to the Indian steel production. And lastly, the single block method, where the blast furnace is cut at the foundation, pulled out, and a new pre-assembled blast furnace takes its place. The shutdown period for this is around 90 days. That means loss of around 0.54 million tons of steel or a loss of around $54 million to the Indian steel market. The options are plenty, but the company needs the one that is the most efficient and incurs the least amount of losses.
The only method which could cater to all these requirements was single block method.
With the single block method, the amount of time spent dismounting the paraphernalia around the blast furnace is reduced, because the new blast furnace arrives pre-assembled. The plan that fits the best was the single block method, which sounded deceptively simple, but was intensely complicated to execute.
When this concept was discussed, it was found that the outage time has been quite low, and it was found that our production would be out of the system for the lowest possible time. So as a result of which, it was said that this is the process that we should adopt.
This is a completely unconventional method. First time it was going to be done in the world actually. But we took actually not a risk, but we took actually a detailed calculation.
But a lot of meticulous planning have gone into it. People sat together, they did micro planning, macro planning, and whatever risk, how we can mitigate those risks was also planned and put it on a piece of paper.
It's been in our DNA to take routes which have not been maybe tested before.
There is always risk attached when you're doing something new. And that's where JSW is very good at. We like to do things which is first time in the world, so this was one of those, and we said, okay, let's go for it.
JSW, India's largest steel producing company, decides to go for a heart transplant. But with untested equipment, new surgeons, and a method to carry out on a massive scale. It's a decision to replace the 9,000-ton giant with another 8,800-ton structure by a method that is unique and at a grand scale. But first, to reach the top, the team will be hitting the bottom. Too much to do and too little time. The team has a gargantuan task ahead of them, and they go at it with blazing guns. But while clearing out a path to success, how many more obstacles will come their way? Because there seem to be one too many. One of the largest steel manufacturers of the country takes one of its vital steel plants and decides to try an unconventional method on a humongous scale. Replace a 9,000-ton blast furnace with an 8,800-ton furnace.
We like to do things which is first time in the world.
A project of this scale and ambition needs all hands on deck. Multiple teams are set up to carry out tasks simultaneously, so production doesn't have to stop. The team has set 90 days of shutdown, which means that the surrounding work that accompanies the blast furnace exchange needs to start now. They have to start preparing the plant to fit the requirements of the new blast furnace. A time map is drawn out with the number of days each process requires. Each process can take anything from 50 days to 200 days to finish. So the team decides on an ambitious 250 days until shutdown. Add to that the 90-odd days of shutdown, which can potentially stretch the project to almost a year or more, given everything is completed on time. The team comes up with a 4-step process to dial up the efficiency. 1. The cleanup, which involves clearing out the area to accommodate space for new construction. 2. The preparation, which involves setting up the systems to carry out the single block replacement method. 3. The execution, which is the final furnace exchange. And 4th, the commissioning. This is where the new blast furnace will be tested. Then there are the subparts. The cleanup comprises of 2 steps. Land inspection, checking the soil condition of the site if it can hold the weight of heavy structures. Space accommodation, creating space for the construction of the new blast furnace on site. To carry a mammoth on your back, you've got to have a backbone made of steel. The Dolvi plant is going to build a mega structure on its surface. But will its surface be able to take this weight?
Since it is just next to the sea, the soil conditions are very soft.
So if we place any load on this soil, it will sink.
Soil strength of any land is measured by a parameter called the soil bearing capacity, or SBC. If the SBC of the soil is less, then any heavy load placed on the soil will sink. For construction of colossal levels to take place on this soil, the land has to be treated first.
We bore a drill right up to the rock.
After that, TMT steel bars are inserted and concrete is poured from the hard rock right up to the top of the surface. This process is called piling, a method used to strengthen the ground on which construction needs to take place. But the team will have to hold the drilling a little bit longer because the area where the new blast furnace needs to be put together is a little crowded. Which brings us to the next stage, space accommodation.
The area is very congested, so we had to create a space for the new furnace to be built. This we could accomplish by diverting railway track.
A rail route is passing through the area, which will soon be taken up to construct the new blast furnace. This rail route carries locomotives that transport molten hot iron from the blast furnace to the steel melting shop. But now this train needs to be taken off tracks. The train tracks are to be rerouted. But one last obstacle still stands in the way: the slag unit.
As far as the production of iron is concerned, it is always accompanied by a byproduct which is called a slag.
Inside the blast furnace, when molten steel is churned, it leaves behind a stony waste material called slag. But the slag can't entirely be called waste. If repurposed correctly, it can be used to make cement, for which the blast furnace sends the slag to a slag unit. But this slag unit is now standing in the space where the new blast furnace will be assembled. But just removing it isn't the solution.
When you are doubling the capacity of the blast furnace almost, then obviously the slag associated with it also becomes much more.
The team needs to double the capacity of the new slag unit. So the old slag unit is demolished and two new slag units with advanced technology are established. With the slag unit out of the way, the rail rerouting proceeds smoothly. The ground has been cleared and strengthened. Cleanup is declared successful. Meanwhile, the new blast furnace is being created. The area wears a busy look, with hundreds of workers and team from two different countries working towards a Herculean task. The engineers realize that the new blast furnace is turning out to be much more high maintenance than they expected. The team starts to work out how to manage the heating needs of the new furnace without altering their steadily mounting costs.
The temperature inside the furnace can go as high as 2200 to 2300 degrees centigrade.
And to fit the demands of this new furnace, the whole plant will need an overhauling. But is the team up for this massive renovation of the entire Dolvi plant? The team decides to try a unique method for its furnace exchange. The prep work has begun. The foundation of the Dolvi plant has been strengthened. The construction roadblocks have been removed. But the team realizes that their new furnace might turn out to be a white elephant.
Apart from the size of the blast furnace, we have so many things which are very much advanced, what we did in the new blast furnace.
The new furnace comes with its own set of improvements. A better cooling system, a better energy efficiency system, and a better dust extraction system. But with the increase in performance and increase in size is a logical outcome, which leads to its own complications.
The temperature inside the furnace can go as high as 2200 to 2300 degrees centigrade.
To maintain this scorching temperature, the furnace uses stoves. The old blast furnace had 4 such heating stoves. But to keep the newer, bigger blast furnace running at 2200 degrees, it needs something extra.
So the solution was to put a 5th stove and connect it with the existing system.
Part by part, the 5th stove is directly erected at its allocated area. With 42 meters height and 6,500 square meters total heating area, the 5th stove is now standing in its position. Not only does it give the new furnace more heating power, it is also more energy efficient. The new furnace keeps shaping up to be bigger and snazzier, putting in more pressure on its connecting units. The auxiliary units of the plant need to be upgraded to suit the demands of the new blast furnace. Its stock house and cast house will have to be expanded. The process that precedes the raw materials going into the blast furnace is collecting the raw material. The raw material for steel is housed and prepared in a unit called the stock house. It's like a kitchen where a balanced diet is prepared and sent to the furnace. This diet involves proper proportions of coke, iron ore and lime, the basic raw materials for steel making. These materials are sent to the furnace using conveyor belts that connects the stock house to the blast furnace. But a bigger stomach needs a bigger appetite. And therefore the stock house now has to be expanded. So another unit is added to the back of the stock house to increase its capacity. At the bottom of the blast furnace is the area where the molten steel is released from the furnace. This unit is called the cast house. The cast house works as a steel bending machine. Like the taps of a soda machine, the cast house taps out molten steel through its tap holes. To keep up with the size of the new blast furnace, the cast house also has to be expanded.
The old blast furnace, designed in early 70s, had a sloping cast house. This sloping design didn't allow any mobile equipment to work in the cast house.
Working area at the top of the cast house has to be flat to make things easier for maintenance and other things.
The team wants to build a safer, more convenient cast house with a level floor. For that, first the base pillars are strengthened. Second, the supporting structures are removed. And third, the roof of the cast house is increased to level it into a flat surface.
This was accomplished with a unique engineering design where we didn't dismantle the cast house, but we surrounded the columns with support structures, and then we cut them, and with the help of hydraulic jacks, these columns were lifted millimeter by millimeter till we achieved the target.
The team succeeds. The battle is won, but the war is still looming ahead. Because as time passes, we are now moving towards the blast furnace shutdown, after which the old furnace will take its final breath. Now the team has 200 days till shutdown.
The kind of EBITDA margins which you would see in terms of dollars per ton would be, let's say, varying between $100 to $135 a ton. At that time, we must have been producing about 5,000-6,000 tons a day. So you would lose almost, if you multiply that by $100, then you would lose that much per day.
There's not a moment to lose. It's time to set up the building blocks for the main event, the furnace exchange. The team moves to the next level, preparation. And now the action trifurcates. Preparation stage is a 3-step process which has to run simultaneously. First, the base cutting of the furnace, where the old blast furnace is detached from its foundation. Second, a skid platform is to be constructed for the furnaces to slide. And third, the new blast furnace construction. Attempting a mega-scale single-block method. Sounds ambitious. Having more than 1,000 people working around a molten steel churning vessel sounds risky. But cutting the base of a furnace while it is still in operation sounds insane.
There were huge potential for accidents.
The safety in any case, we can't compromise.
So we put together a team of safety professionals to take care of the safety issues.
The team came up with a safety plan. But even with the safety measures in place, base cutting is going to be risky. But first, they need to decide where they can aim to make the first cut. When measured from the ground level, the new furnace will fit in 3 meters taller due to the adjoining machineries. This makes the angle at which the conveyor belts connect to the top of the furnace much steeper, which will make the raw materials to roll back. So the team decides to take the new furnace 1.5 meter deeper into the foundation, adjusting the increase in height to just 1.5 meters above the ground. The team can breathe a little easy, now that their raw materials will be roller coasting straight down into the steamy blast furnace. Onwards to cutting the base of the old furnace. This is the point from where a 9,000-ton old blast furnace gets slashed from its foundation. A furnace that is fully functional and carrying thousands of tons of molten steel.
The method involved drilling a hole across the foundation from one end to the other end. We drilled such 2 holes.
This method also uses diamond-embedded wires for cutting. The method involves drilling cylindrical holes across the base end to end. The team has to be very steady with the drilling machine.
We are cutting across a foundation where the accuracy of deviation had to be limited to only 3 millimeters.
If they deviate any more than 3 millimeters of the calculated mark, there is a possibility that the whole structure will get stuck. The pieces between the holes are removed, and specially designed steel plates are inserted and carefully welded. This is repeated until the entire 9,000-ton furnace is standing on giant plates of steel embeds. It takes 200 days, but thanks to the carefully calculated base cutting technique, the steel-making giant is finally off its base. It brings a long reign of 15 years to an end, as the aging monarch leaves its throne to be taken over by a younger, stronger successor. The team bids farewell to its old furnace that has steadily served the Dolvi plant for over a decade and a half. Meanwhile, giant ring-like pieces are taken to the assembly area, where they are put together to be assembled into the new blast furnace. To carry a structure of this tonnage is not something that is possible for a normal truck. Special multi-axle wheel trucks were brought into the scenario and assembled on the ground. These multi-axle wheel trucks are 119 meter long and can take up to 1200 tons of load and are extremely suitable for an extreme engineering project like this. To move such gigantic structures requires utmost care and patience. Even the slightest mistake can prove fatal. The old furnace is off. The new one is ready and raring to go, waiting to take its rightful place in the Dolvi plant.
People didn't sleep all night.
We all had some apprehension that it may not come out from the original position.
It's now time for the massive furnace exchange. Will these 9,000-ton heavy Goliaths move? The 9,000-ton giant, gurgling gallons of hot lava inside, is cut off from its foundation. The old faithful furnace is finally put to rest, and the countdown for shutdown begins. Both the new and old furnaces are now sitting on giant steel plates for their transfer. They will have to slide onto a skid platform that will act like a moving walkway for these enormous structures.
If you look at glass, it's very easy to slide paper on the glass surface as compared to sliding the paper on soil. This being the concept, we tried to make the surface as smooth and as possible.
The Japanese team recommends Teflon, a material specially designed to make the surface extremely smooth. Nippon had successfully used it earlier on their skid platform to make the furnaces slide. But the move has to be precise. Any variation in the slope would result in diverting the path of the furnace.
The effort was to keep the variation within 1 millimeter.
The transfer of the Titans is about to begin. But precision is key. Every inch has to be constantly observed. Every move has to be authenticated. The team will have to keep an eye on each and every corner of the platform. The new furnace is almost ready, eagerly waiting to take over the throne. The engineers give it its final touches. Now, to pull the old blast furnace out, a pulling mechanism has to be established. The blast furnaces are each almost 9,000 tons heavy, which makes them over 8 million kilos. And to move these giants, one needs a force as strong. This force comes in the form of hydraulic strand jacks. They are placed next to the skid platform. These are the hydraulic systems that will generate enough force to pull out the furnaces from their positions. This force is then transmitted to the furnace through a series of wire mechanism comprising 32 wires each. First, the old furnace will be pulled out of its position, and then the new furnace will be pulled into its place. For this, 3 anchors are strategically placed at 3 points.
First anchor was to pull out the old blast furnace. Second anchor was to pull out the new blast furnace in line with the old foundation. And the third anchor was to pull the new blast furnace onto the final platform.
The moment has arrived when the team will endeavor to make the giants slide. There is one question on everyone's mind. Will the furnaces move?
I still remember the day when the movement was about to be done and the tensioning of the wires were going on.
If I correctly remember, it was on 27th November 2015.
People didn't sleep all night.
We all had some apprehension that it may not come out from the original position.
With a heave-ho, the process starts, and the transfer of the Titans begins.
Finally, there was a big, kind of excitement when it moved its first millimeter.
That was the most exciting moment for me and everybody in general.
The team is ecstatic. They are watching the result of their efforts right in front of their eyes. The 9,000-ton mammoth is finally moving. The old furnace is pulled out successfully. The first move of the single block method is complete. But this is not the time to rest. The team gears up for the next act. It's time to move the new furnace onto its place. The anchor breaks.
When we started pulling the new blast furnace, the anchor came off from its support structure.
A huge hurdle. Just when they were so close to the finish line. But will this break the team's spirit? Will the team be able to come up with an engineering miracle at the last moment? The team racks their brains to come up with a quick solution for the anchor failure. Will the new furnace be pulled into its position in time? Because the clock is ticking. After months of hard work, the old blast furnace was finally cut off its base, placed on steel plates, transferred onto a skid platform, and finally moved out of the way. But the new furnace decides to throw a tantrum, breaking everyone's confidence and its own anchor. The ship was about to reach the shore when the team met with a hurricane. But the team is determined. The anchor mechanism had broken, but their resolution is still standing strong. The team goes back to the drawing board.
We had problem with the second anchor position. When we started pulling the new blast furnace, the anchor came off from its support structure.
The pulling mechanism consisted of two parts, the hydraulic strand jack and the anchor. The anchor was a mechanism that gave stability and support through its plates that were inserted into the foundation. But the welding that was to keep them together was weak. Under the excessive load, the base plate toppled.
We are having two support, and yesterday we were pulling the furnace, so this foundation came out.
After a long discussion, the team finds a solution. The base plate of the anchor will have to be removed and the concrete surrounding the anchor will have to be dug. A thicker base plate is cut and placed to strengthen the base. To give additional strength, one more base plate is added to the top and welded. But the clock is ticking. Precious time had already been lost. And in this case, time literally was money. But the team is resilient. They are confident about their new anchor.
This is a big setback for us. I believe we should be able to contain this in less than 3 days.
They cannot afford another anchor failure, so they decide to strengthen the remaining anchors as well, just in case. The anchor is repaired and the pulling resumes. History is being created in front of their eyes. The new furnace starts to take slow but deliberate steps towards its rightful place. And then finally, it is sitting on its throne. The biggest challenge of the project, the massive furnace replacement, has finally been accomplished.
This is a very, very unique and innovative approach of construction and revamping of the old plants.
With the new furnace in position, a huge part of the battle is done. But the climax still remained, the commissioning. Now in its correct position, the new furnace has to be tested for proper functioning.
Blast furnace being a very complex system, we run different tests for more than 72 hours to make sure that everything is working perfectly.
This is where the team is going to get an answer. Was months of hard work going to pay off? The team stands back with their breaths held.
You know, there is a tradition in the blast furnace that you light up the blast furnace through the tour, like a mashal.
Over the next 72 hours of intense testing, it is confirmed that the new blast furnace is finally working.
When finally it happened, then there was a great sense of relief that whatever we set out to, we have achieved that.
It was a really big achievement, you can say.
With its strong grit and an objective to win, the team has succeeded. The hard work has finally paid off.
So there was all the people who had built it, all the Japanese and the Indian experts, and it was quite an exciting moment. And we have done a number of blast furnace startups, but this was very special.
It has been a very learning and humbling experience for me.
It's not about profits or it's not about capacity. It's the challenges which keeps us going. There were a lot of hiccups. Things would fail. When finally it happened, then it's like a dream come true. It's like a magic that happened.
We are bringing in specific aspects of environment, how the steel is produced in an environmentally sustainable manner.
India is a very large country with a large number of people residing in this country. We have just started scratching the surface. I will spend all my life building steel plants, still will not be able to complete the unsatiated demand for India.